This is part 1 of the series Similarity. And as the name implies, we're going to be discussing similar figures. If you remember the idea of similarity when we were dealing with dilations, we talked about figures are similar if there exists a similarity transformation or composition of transformations that maps one figure onto the other. If we take a look at these two figures, we can see that they have corresponding congruent angles, but they're different sizes. So that's the general idea behind similarity. Similar shapes have the same shape, but different sizes. The implication there is that the corresponding angles of similar figures are congruent, and the corresponding side lengths vary by a scale factor, a common scale factor. Now this brings up the additional idea that similar figures have proportional side lengths. We're going to be looking at this in great detail in just a couple of minutes. But I first want to point out that we have two major pieces of information that we're going to need to be able to analyze and solve problems of similar figures. The first one is the similarity statement. Here is a similarity statement. Polygon ABCDE is similar to polygon A prime B prime C prime D prime E prime. The similarity symbol is the tilde standing by itself. Notice in congruence we had an equal sign with a tilde over the top. In similarity it's just the tilde and no equal sign. So this polygon is similar to this polygon implies that all the corresponding angles of this are equal to the corresponding angles of this. And how do we determine that? The similarity statement gives us the order of correspondence. So vertex A corresponds to vertex A prime, B to B prime, C to C prime, and so on. So the position of the vertex in the similarity statement tells you the corresponding vertex in the other figure. Likewise, we can pair up vertices to get corresponding sides. For example, AB corresponds to A prime B prime. So the first two letters. Likewise, CD corresponds to C prime D prime. It's easy in these two figures because I named them very similar names with just a prime tacked on. But you're not always going to have that. But this relationship will be true, that the third position corresponds to the third position, the fifth to the fifth, and so on. That means angle A is congruent to angle A prime, B to B prime, and so on and so forth. Now the second major piece of information is called a proportionality statement. And the proportionality statement tells us that the ratios of any two corresponding sides in these similar figures is proportional, or the same ratio. Now if you remember, the ratio of any two side lengths, corresponding side lengths in these figures was called a scale factor. So the scale factor for these values must all be equal. So AB corresponds to A prime B prime. So the ratio of AB to A prime B prime must be equal to the ratio of BC to B prime C prime, and so on. So the ratios of all corresponding sides must be equal. And that is what makes this a proportionality statement. So we have two major statements. The similarity statement that tells us the correspondence of the figures, and the proportionality statement, which tells us the relationship of the sides. Let's go ahead and explore this idea in greater detail using a specific example. Here I have two triangles and a similarity statement that says triangle ABC is similar to triangle XYZ. This statement tells us two very important things. The first is that the measure of angle A is equal to the measure of angle X, the measure of angle B is equal to the measure of angle Y, and the measure of angle C is equal to the measure of angle Z. So this angle is congruent to this, this to this, and this to this. The second major thing it tells us is that the ratio of AB to XY is equal to the ratio of BC to YZ, which is equal to the ratio of AC to XZ. Let's go ahead and take a look at that specifically. So AB to XY is 12 to 18, which simplifies to 2/3. And BC to YZ, BC to YZ is 6 to 9. So 6 divided by 3 is 2, and 9 divided by 3 is 3, so those are the same. And then AC to XZ, which is 8 to 12. 8 divided by 4 is 2, 12 divided by 4 is 3. And we can see that these ratios are all the same. You'll remember that this ratio, the ratio of two corresponding sides, is the scale factor. Now, remember that scale factor was the ratio of two corresponding sides, and it's destination divided by source. So since we have 12 divided by 18, it's the scale factor from XYZ to ABC, which means that ABC is 2/3 the size of XYZ. If we multiply 18 by 2/3, we would get 12. 18 times 2 divided by 3 is equal to 12. Same thing with 12 and 9. So that's the idea of scale factor being the same. So the ratio of any two corresponding side lengths is the scale factor. We could have flipped these ratios and said the scale factor from ABC to XYZ, we would have gotten 3/2, 3/2, and 3/2. Just take the reciprocal of each one of these ratios, and you would have gotten the reverse scale factor. So just as a recap, the scale factor from ABC to XYZ is destination divided by source. So we could have said 18 divided by 12, which would have given us 3/2, which means this is 1.5 times bigger than this. 3/2 is 1.5. We could also say the scale factor from XYZ to ABC. Again, we can use any corresponding side length. So here we could use 9 and 6. So it's destination 6 divided by 9, which reduces to 2/3. So that's scale factor in both directions. Again, with these proportionality statements, the fact that the ratios of any two corresponding side lengths are always going to be equal, it doesn't matter which one of the corresponding side lengths we use. Now, there's an important idea embedded in here that we've just touched on, but I want to get into it in a little bit greater detail. We've had the luxury of having a similarity statement to guide us into the correspondence of these different sides and vertices. So the idea of how to verify that two ratios are in proportion to one another becomes important. Now, it's obvious for these. If we take any one of these, we set up 2 is to 3 as 2 is to 3. And it's very obvious that 2/3 equals 2/3. But the formal way to verify this is called the equality of cross products. What we're going to do is multiply the denominators of both sides by the opposite numerator. So 3 times 2 and 3 times 2, which gives us 6 equals 6. Now you may say that was pretty silly. Of course these are equal. But perhaps we get something that looks a little bit different. Let's say in working out our values, not with these triangles, but with some example, you come across a ratio, a set of ratios like this. 7 is to 4 as 22 is to 12. It might not be intuitively obvious to you whether or not these are in fact equal and therefore a true proportional. So let's take the cross products. 7 times 12 is 84, and 4 times 22 is 88. And you can see that these are not equal, so this is not a valid proportion. This is not a valid proportion because the equality of cross products was not maintained. But let's alter it so that it is. So if we said 7 over 4 equals 21 over 12, 7 times 12 is 84, and 4 times 21 is 84, and they are a valid proportion. Now there are several manipulations that we can do on proportions to create a new true proportion, that is, maintain the equality of cross products. In looking at proportions, there are several values that are important. This would be called the first proportional, second proportional, third proportional, and fourth proportional. The second and third proportional values are known as the means. We're going to look at the means in much greater detail in a future unit. But for now, understand that those are the means, and the first and fourth are called the extremes. One of the manipulations I can perform is I can swap the means. For example, I can say 7 is to 21 as 4 is to 12. And again I have 7 times 12, which is 84, and 4 times 21, 84. So I've swapped the means. I could also swap the extremes. I can say 12 is to 4 as 21 is to 7. And again, we still have this 7 times 12 and 4 times 21. I can flip them top to bottom. I can say 4 is to 12 as 7 is to 21, and I still maintain that equality of cross products, and I can swap them from side to side. I can say 21 is to 7 as 12 is to 4. And just as an aside, probably one of the most peculiar of the manipulations that you can perform to create a valid proportion is you can add the denominator to the numerator of each expression. You can say 7 plus 4 over 4 equals 21 plus 12 over 12. Now taking these cross products, that would be 11 times 12, these two, and 33 times 4, which is 132 and 132. Doesn't matter that the values aren't 84 anymore. It's still a valid cross product because this equals this. So this is a true proportion. All right, let's continue with this idea of similarity with an example that solves a particular problem.